Good morning, everybody. And I'd like to start just by thanking the network for giving me the invitation to speak today, and also for funding some of the work that I'm going to be talking about this morning. So definitely thank you very much for that. As a little bit of background, I'm a theoretical chemist, typically working in electronic structure theory. And I would say that this optimization has been kind of a theme running throughout my work since my PhD days. But it was maybe traditional optimization, so simplex and BFGS optimizations. And what I'd like to spend some time telling you about this morning is how we're starting to introduce AI into that. And I'd like to think that I'm on brand in that AI here isn't just meaning artificial intelligence, it's also automated investigations and those types of things. And I would say that some of the results that I'm showing today are kind of preliminary results that we haven't published yet, so please bear with me with this, and I'm going to leave out some of the technical details just until we get things really nailed. So we have two main strands that I want to talk about this morning. So one is design of new materials, which fits in nicely with some of the rest of the themes today, and also tell you a little bit about some method development within quantum chemistry, some of the new tools that we've been developing using AI techniques to do that. And I'll start out with the network-funded project, which we called Optimizing Flatland. And what we were trying to do here is predict some new functional materials. And we did manage to assemble a kind of a varied team of people to work on this. So we had people who were interested in data in chemistry, we had theoreticians, and we also had an experimental collaborator too. So the idea was, can we actually predict something and then make it as well? Just to give a little bit of the background, so I know some of the people in the audience aren't actually chemists, so chemists, bear with me. Everybody else, I guess, here's just some of the background of what we were interested in. And what are known as metal organic materials. The chemists in the audience might recognize these as MOFs, for example. And it fits in nicely if you know anything about graph theory that we've already heard quite a bit about. So we take some metal nodes, and we link those together with our organic linkers or our edges. And depending on the chemistry involved, you can make different types of structures with this. So for example, a cage, polymers, nanosheets. So these are a little bit like graphene type materials. And then there's the famous sort of frameworks. That's the metal organic frameworks, or MOFs. My experimental collaborator here is particularly interested in the 2D materials here. So they're sometimes known as 2D MOFs or metal organic nanosheets, or MONs. And if I talk to my experimental collaborator, they get really excited about these for a number of different reasons, particularly that they can tune these, so depending on the application that they're interested in. They can either chemically tune them or physically tune them. The molecular thickness can be an advantage depending on a couple of different scenarios, and particularly for the types of applications we were interested in, it's also this high surface to volume ratio. Being a 2D material, we really do get that high surface to volume. And again, PowerPoint doesn't seem to want to update. Here we go. So what was the application that we were interested in this case? So kind of looking at the UN sustainability goals, we all know that access to kind of clean and healthy drinking water is a big thing for us on the planet. And this graph that we've pulled from our world in data source here shows just how much our freshwater usage as the planet has gone up over the last 100 or so years. It stops at 2014 here. We can probably predict that it goes up even more. And of course, this isn't just population growing that's gone up. Of course, access to drinking water in our houses and so on has gone up, but it's also agriculture and industry that supports these things. And I guess the problem is that at some point we're going to run out of fresh water to be able to support the growth in population and the growth in industry and so on. So even though our planet's covered in roughly about 70% water on the surface, less than 1% of that is fresh drinking water. So the idea is, can we get fresh water from an unconventional source? What do we mean by unconventional source? Well, one of those is obviously seawater, so we can do a desalination. The other one is, of course, to take the wastewater, which comes from industrial processes, and try and clean that up and reuse that as drinking water. So how do I join these two bits together? Well, The idea is to use the metal organic nanosheets as some kind of desalination membrane. So we construct this atomic thickness membrane, and then the schematic here gives you some of the idea of what might be going on. So we have our dirty water on the left-hand side here, and then we pass it through the membrane, and hopefully we get our clean drinking water out on the other side. And in some ways, this isn't anything new. You can use polymers to do this, and the advantages of using a metal organic nanosheet to do this is essentially we're hoping that we can improve the permeability and selectivity. So can we really just get the water through there and try and eliminate these extra particles which are making their way through? And the idea for this project was, can we design the pore sizes to be the particular size that's going to let water through but stop salt? And can we use an AI to then design these ideal membranes for us? So can we predict the pore size that we need, particularly to do this application of desalination membranes? And so this was the plan in the kind of early days. So this is what we thought we wanted to do. I would say that our project was scheduled to start in April 2020. Probably don't need to fill in the blanks for that one. So the idea here was that we're going to need to construct some data. So can we generate some data? We thought we would use an evolutionary algorithm to do this, to make our data set. One of the reasons for doing that is that these 2D materials are poorly crystalline. So we can't just do X-ray crystallography and get the structure of these. There is some data available, but nowhere near enough to be able to train neural networks and so on. So can we generate some data? Can we then use a generative model to then predict new membrane materials? And that was going to be the main focus of the work. And then the longer term plan was, can we add some reinforcement learning, which Stephen was telling us about yesterday? In some ways, we wanted to try and do this for a synthetic accessibility. So can we make sure that the AI is actually predicting something that we can make? We do actually want to make it, and then we wanted a feedback loop. So can we use then the synthesis and the characterization data to improve our data set and improve the predictions? And so, as I mentioned, we were going to try and focus on this area for this 6-month project that we were funded for. Now, of course, COVID did happen. Grand plans were sort of cancelled, so we had this grand idea that we would get everybody together in one room, all of our collaborators together for an initial Hackfest for a week, which sounded like a great idea. In April 2020, that was not going to happen. We did try and replace it with Zoom, but certainly back in those days, or that phase of the pandemic, we really weren't used with the online working, so it didn't quite happen how we wanted. But Adam, the PhD student who was seconded onto this project, he did dive into this, and rather than using a genetic algorithm to generate the data, as he sat down to try and write that genetic algorithm, he discovered a piece of software that would do some of this for us. So there's this code we found. It's from Randall Snare's group over in America. And he has this code called tobacco, which is topologically based something, which basically tells us they really wanted to call it tobacco for some reason. And what tobacco does is it will assemble these metal organic framework type structures for you. So you feed it some information, it needs 3 different pieces of information, and then it will try to assemble them for you. So there's what they call a topology file, which is sort of a shape template. You provide the nodes, and you provide the linkers, and it will then stick them all together, and it will generate all of the different possible MOFs that come out of your information that you've given it. So I thought, well, great, this is doing part of the work for us. If we can give it these bits of information, we don't need to write a genetic algorithm, it will synthesize the data for us. There were some problems in that, we'll come to them in a little while. One of the other good things it does is that if your nodes and your linkers don't fit that topology, that kind of shape template, it throws it away. It says this isn't going to be valid. So it helped us in the data generation phase. And there's a couple of different ways you can slice this up. This is what the image is trying to show here. So you can either take the metal nodes just as being essentially the metals, or you can use what's called a secondary building unit. So if you're familiar with moths, you'll know a secondary building unit. And so what we did to try and reduce the amount of data that we were generating was that we selected only the nodes and topologies that would lead to a 2D structure. So we didn't want the 3-dimensional MOFs, that's not what we're after here. We only want the 2D ones. So again, tobacco helped us in that respect. We did need to select some linkers to go along with this as well. This is obviously just a very small subset of the linkers that we used. For the chemists recoiling in horror at the xenons and rubidiums on here, I'll explain what's going on there in a second. So what we wanted to do was generate a lot of different linkers which will affect the pore size. So we want linkers which change that pore size. And so here we've got this base linker of these two fused rings. And what we needed to do was, using our kit, we needed to just add some tag atoms which we could then replace automatically. So that's what the xenons and rubidiums are. The xenons are our phases of linking, so that's where the linker will join either to the node or to another linker. And the rubidiums are where we're going to mutate those. So we add functional groups where those rubidiums are. And the functional groups are quite varied, so things from sort of simple-ish halogens right through to fairly complicated hydrocarbons. So we can hang a lot of different things off here. And of course, anybody who's done any kind of cheminformatics or high throughput type of calculations will tell you straight away your problem here is going to be some combinatorial explosion. So we have all of these different linkers that we're trying to mutate. We want to mix them with all the different nodes, all the different topologies. Your data just explodes. So we wrote a randomizer for this sort of proof of concept phase. So it would select a subset of the linkers for us, and then it will go through this tobacco process of joining everything together. Here's the data flow of what Adam came up with. It's quite horrific. We're not going to talk you through every single bit of this, don't worry. So Adam managed to stick and glue everything together and sort of semi-automate this process of generating this big data set. The only thing that we needed to do that kind of isn't semi-automated, he needed to generate the structures of those secondary building units by hand. So what comes out of this, we get lots of crystallographic information files. And one of the problems with using the tobacco code was it doesn't read a CIF file that most other programs can read. It has to be a specific tobacco CIF file. So this is where Adam spent a very long time actually converting a valid CIF file into a tobacco CIF file. So maybe a lesson in there in terms of just grabbing this bit of code from the internet that you think is going to work really well and then finding out that there's something that bites you. It does spit out a HDF5 database of all of these, so Adam again kind of grabbed all of these things back together at the end. And once he'd written this piece of software, in running it in for about 3 hours, you can generate 45,000 hypothetical MONs. So that was just one run of the randomizer. So this is just a very small subset of what we could possibly do. Okay, so that was generating the data. The next part was, can we start to make some AI predictions with this? And again, looking into the literature, we found something which looked intriguing initially. So we found what's known as a MOF-ID. And this is somewhat similar to a smile string for people who are familiar with those. And the reason why you can't just use a normal smile string, of course, is that this is a periodic structure. So we need to be able to join them together. And so essentially you have something that looks like a smile string for the metal nodes. You have a smile string that looks for the linkers, and then you add a topology on the end. And from what we know about smile strings in, for example, drug design, we thought, okay, can we use this and do something similar to try and predict new materials in terms of these MOF-IDs? Again, I'll spare you some of the technical details. Adam is here in the audience if anybody does want to have a chat with him about it. And I think yesterday from Joe's talk, we learned that LSTM, the long short-term memory models, is possibly the worst named of all of the different possible models. So essentially what we're trying to do here is encode the MOF-ID, decode it, see whether we can actually predict these things. And in the scope of the time that we had for this project, this was our input from our validation set. So this was sort of unseen data for our network. This is what the MOF-ID looks like, so you can see it's actually fairly complex. And what came out, well, it wasn't that good, if we're honest. We can see it's learned some of the features. So for example, it does have the metal in there. It's learned that brackets are very important. It's learned that carbon might be important. And it's given us something that looks a little bit like a topology at the end, but not really. So it's managed to learn some of the features. We could obviously do a lot more work in terms of improving this model. However, looking back on it, and we're still kind of working on this problem, we think we're actually trying to learn too much here. So, for example, this topology file, it's just a string of 3 letters, but it's encompassing the whole shape of your structure here. So trying to actually learn that indirectly through just this MOF ID, we think is actually probably the wrong path to take. We also have one of the problems that we've already discussed in this meeting about smile strings, in that it's very easy to generate something which isn't valid. So this thing up here, this isn't a valid MOF ID in the same way that you wouldn't always get a valid smile string. So in terms of what we've actually learned from this part of the project, we've got together this software pipeline so we can really easily generate a lot of data for these MON structures. We've got that database together. And while the MOF ID is actually really good for our database in terms of we've now got an identifier which goes along with each one of those structures, it's probably not a good representation for machine learning. So what are we doing now? Well, we're now looking at graph-based representations. And so my colleague Patrick Fowler, who's done a lot of graph theory, is actually looking into this with us. We're looking to improve our pore size predictions, which come out. So can we use machine learning to actually predict the pore size? And then we're also still generating more and more data, so more hypothetical MONs. And my experimental collaborator, he has got the equipment set up so we can test whether the desalination membrane works. So as soon as we get our first predicted MON, we are ready to give it to him and he will test it for us. Okay, I'd like to change tack slightly there now as well. So to tell you a little bit more about how we're using AI in other ways. And this is more in terms of the tools of quantum chemistry. And so a lot of work that's been done with machine learning and quantum chemistry is trying to bypass the Schrodinger equation. So it's been, let's do away with DFT and let's just try and predict what would come out of DFT. We're taking a different approach, and what we want to do is use AI and machine learning tools to improve the DFT calculations, or the electronic structure calculations. And in particular, what we're trying to do here is look at the basis sets used in quantum chemistry. So this is my favorite molecule here, and you can see the highest occupied molecular orbital. Underneath there, that's caffeine. I could certainly do some more of that this morning. And what the basis set does, essentially, in this simple linear combination expression here, the molecular orbital is made up of contributions of these basis sets. So this basis set part of an electronic structure calculation, it's really going to dictate the quality of your wave function and whatever you get out of there, so be it an energy or other molecular properties. Just choosing your basis set is something of an art form. It's something that you build up with a bit of experience of running electronic structure calculations. And it's even harder to develop new basis sets. So what we thought was, is there a way that we can start to come up with new basis sets using machine learning techniques? Just to give you something of the conventional workflow here. If you want to come up with a new basis set, essentially you come up with the idea, so you try and design something, you optimize it, you have some kind of test set, and then you sit back and you think, has this worked? Usually on your first run round, the answer is obviously no. So you throw everything out, you redesign it, you re-optimize, and so on. And although the optimization, we're using a computer to do that, using fairly traditional numerical methods, we like to think of this as really, this is being optimized by hand. So the human input into this is a lot. We typically can only do this for atoms. It's very painstaking. It takes you several years to come up with a new basis set for a single element. And then you need to pass that out to the other elements that are close by. So my first thought was, having developed basis sets for the last sort of 20 years, can I put myself out of a job by automating this optimization? So there must be a better way of doing this. If we do that and we generate a lot of data from it, can we learn something just from the data? And if we as humans can learn something from the data, can we start to use machine learning to even more put me out of a job and start to predict optimal basis sets? So Robert Shaw is the postdoc who's been working on this. And again, Robert's in the audience. If you've got any kind of technical questions, I'm sure he'd be very happy to chat to you about it. And he went away and he very quickly actually wrote an automated optimization program. We didn't know how to show code in an image really that was engaging, so here's just a screenshot of a GitHub repo. But this is doing a little bit of a disservice to what Robert's done here. So essentially what you can do is, instead of working just on atoms, which is what basis sets did before, you can now optimize on a molecule using this automated optimizer. You simply specify your molecule, what kind of quality you want of a basis set, which method, so Hartree, Fock, DFT, and so on. Press go, and it will automate that optimization for you and spit out a basis set. And Robert's linked this to several different quantum chemistry programs. So for example, Psi4 is one of the ones that we're using in the background. It's fairly easy to add extra ones. And does it work? Well, the answer is yes. So I would say that it's important to stress here, so how basis sets have generally been done is that they are general purpose. You can use them for any different application. What we're doing here is trying to optimize for specific situations. So in this case, we've stolen some molecules from GDB9, and they're just fairly simple molecules containing C, H, and O. So some fairly simple organic chemistry. Can we make better basis sets compared to these famous correlation consistent ones? And hopefully if you squint at this distributions over here for a while, you convince yourself, actually, yes, you can. So this 0 here would be just giving you the same as the existing basis set, re-optimizing it specifically for molecules and organic chemistry. We see this improvement. And we can see it's bimodal. So we've got a nice peak here, nice peak there. Seems to be favoring carbon in its improvement. It's maybe not so surprising because carbon is actually the most prevalent of the heavier atoms in there. We couldn't come down to any reason by why different molecules fall into each of these different parts of the distribution, or the different bins that are in there. However, what we did find is that if you use sort of similarity indices from cheminformatics, you can actually predict whether which molecule, if you give a molecule, you can predict with a simple machine learning model which one of those two bins it's going to fall into. So there's definitely something interesting going on here. Something physical going on as well. If we look at the exponents of the basis set, this is getting maybe a little bit too technical for those who aren't overly interested in basis sets. But what's happening is the basis sets themselves are becoming tighter or more contracted. So the orbitals are actually becoming smaller as we optimize for molecules rather than atoms. So Robert sat back and thought, like, okay, can we start to predict this using machine learning? Because there must be something in there if we can start to predict which molecules are going to fall into the different bins. And so here's his kind of data flow. We won't go into all of the different bits here. And again, I'm sure Robert will be happy to answer any questions you have on it. But here's some initial results that we had from this. And so over on the right here, this is essentially the same figure we had before. This is what comes out of the automated optimizer. And here's what comes out of the graph neural network. And thankfully, somebody's already talked about graph neural networks this morning, so we don't need to go into that either. And the really interesting thing here is, if you look on the x-axis here, it's actually better than what comes out of the automated optimizer. So the graph neural network can predict better basis sets. And at first, we were thinking, well, what's going on here? This doesn't seem possible. But after a little bit of thought, what we've realized is that in this case, what's happening is they're getting stuck in a local minimum. So the automated optimizer gets stuck in the local minimum. And over in this case, the graph neural network, because it's not optimizing in the same way, it gets over to what looks more like the global minimum. So it's actually, in some ways, it's being a bit smarter than we are, and it's doing better than what the human can, which is pretty great. Again, we can look at the exponent comparison. And it's doing something similar to the actual optimized values here. So again, it's making everything a little bit tighter. And so I think there is a lot of room for machine learning and artificial intelligence approaches within this basis set optimization. But I did want to give just one little warning about not always using machine learning. And so if anybody's used PowerPoint recently, as you start typing, it tries to come up with some suggestion of what your slide should look like. And so I started typing the title of this slide, and at that point I just wrote exponent comparison, and this is what PowerPoint gave me. I think it's both cute and terrifying at the same time, and I'm not sure what it's got to do with exponent comparison. But. Okay, so just to summarize this phase of the project, we are able to learn the form of basis sets and basis functions for these different applications. So we think we've ticked off that objective. We do have some evidence that it's doing better than what we would do ourselves, so it's avoiding the local minima problem if we use machine learning for this. And so one of the things that we're thinking about now is, other than just the energy, can we predict a basis set for specifically other properties? For example, maybe polarizability, if we're interested in kind of the permittivities and the dielectric constants that we're already hearing about today. I would like to thank a number of people for this. So Adam was doing most of the work for the desalination membranes, so he's a PhD student in my group who's seconded onto that. Jono was our experimental collaborator. Patrick is doing a lot of graph theory. Payman, who's in chemical engineering in Sheffield, who's got a lot of interest in data and chemistry. The fabulous Kim Jelfs at Imperial was our kind of external collaborator on this too. The basis set project, that's all been done by Robert Shaw, and some other group members who are also working on data or machine learning type projects, Jasmine and Harry, who are also here. Thank these people here for funding. NVIDIA have given us a bit of hardware, and I'd like to thank you for your attention. Thank you.